Thanks, Diego. Thanks for the introduction. You make it sound like I'm always late, right? um, okay. Is this okay? I guess this is for recording, right? Okay. So yeah, welcome to these series of 5 lectures that we have this week. So I know it's kind of, you come in, the lecture has already filled up half the board, right? It's horrible. But this is the less important stuff, right? So this is the outline of roughly what I'm planning to do. So today we'll be talking about the kind of the basics of gravitational waves, how they propagate in vacuum, and some subtleties about gauge fixing and different frames, which then is kind of important as we progress, that we kind of really have the basics solid. And then tomorrow we'll talk about how sources can emit gravitational waves, and we'll also kind of slowly be making our way towards being able to describe the stochastic background of gravitational waves. So that's the typical type of gravitational wave signal that one would be looking for when really is looking for cosmological sources, as opposed to the astrophysical sources that LIGO has already seen. Then we'll talk about some concrete cosmological sources, and finally, well, if time works out the way I'm hoping it will, we'll have time to talk about some experimental challenges, in particular in future detectors. I'll tell you a bit about kind of what sort of data we're expecting to get in the next couple of years and what sort of questions we hope we'll be able to answer. And also what sort of challenges are still open, right? So where we need smart people doing smart things to actually be able to do the physics that we're claiming that we hope to be able to do. Because there really are still a bunch of open questions here. So I also gave you a bit of literature. So I very strongly recommend this book by Michele Maggiore, since this is recorded, right? So if you cannot find this book in your local library, right, this is a shorter version of it, but available on the archive. This is a review dealing particularly with the stochastic background, and also how to describe the responses of different instruments, but in a very theory-based way. And this is a review on different types of cosmological sources. And I mean, this is the rough idea, but I mean, it really all depends on you, because I'm giving this lecture for you, right, not for myself. So, do interrupt me, ask questions. We can adapt the schedule. If there's a particular interest in some subject, we can go slower, we can go faster. So yeah, do ask questions, do interrupt me. What about the size of the writing? Can you read this? Okay, if I get smaller and smaller, right, let me know. Okay, so let's start with some motivation. Motivation about the question, what gravitational waves, how the word gravitational waves is actually connected to the word early universe in the title, right? So why do we think that gravitational waves are an interesting way to probe the early universe, to probe particle physics of the early universe? And so you've possibly all seen kind of the picture of the evolution of our universe, right? So we have time, or 1 over temperature, going to the right, and then we have the Big Bang, and then the expanding universe. And we have different epochs, right? We have, for example, BBN at some point, right? And we have CMB at some point. And a lot of things that we know about the history of our universe, and a lot of things that we know about particle physics in general, we know by observing photons, okay? So if we have a photon, we can probe all the way back to the time of the CMB, and we can learn about the history of the universe from the time of the CMB on, so when the universe was 1 eV or colder. But we cannot really go earlier, because at earlier times the universe was not transparent to photons, and so kind of all information is lost because the photons get rescattered. So if we want to probe earlier, right, meaning earlier in time, meaning higher in energy, we need some sort of messenger that interacts more weakly than photons with the ambient matter, right? So we could do neutrinos, in principle. If we could do neutrinos, that would get us a bit further, right? It would get us kind of close to BBN. But that's also hard, right? Because then you need to detect the cosmic neutrino background, right? Which is not also something we haven't achieved yet. Or if you want something which interacts even more weakly, you can go for gravitational waves. Gravitational waves, so perturbations of the metric, they interact so weakly with absolutely everything, right? That even if they're produced here at the very beginning, right? Even during this phase of inflation that you heard about last week, right? They can go through the entire universe essentially unperturbed. And if you detect them today, you can not only learn something about the source, but you can also learn something about the entire cosmic history, because gravitational waves being radiation, they get redshifted as radiation. So depending on the equation state of the universe, depending on the expansion history, different things will be imprinted on the spectrum. So that, in theory, is the promise, right? This is why it's interesting. This is why particle physicists like me are interested in gravitational waves. The problem, of course, is that if the gravitational wave goes through the entire universe without ever, caring about anything, it will likely also just go right through your detector, right, and not do anything in your detector, right? So the challenge is to actually make the detection here and to detect this extremely weakly interacting messenger to then learn something about the history. Yes? No, that's simply the statement that that gravity is weak, right? The way that the gravitational waves interacts with matter is through gravitational interactions, and gravitational interactions are just so much more weaker than any particle interactions. Right, this is why it's so hard to detect them, right? They are very weak, right? So it's not a question of frequency, right? So the fact it's okay. It's the thing that the amplitude is very small, right? Because again, there's a 1 over m Planck, as you say, in the generation, right? But then also the interaction between this and matter is weak, right? Because it's a very small perturbation of the metric, and that's mediated to any particle physics processes just via gravity, right? So, but the kind of it's a good thing and a bad thing, right? It's a good thing because it means they're never in thermal equilibrium, right? So we don't have the problems that we have with the photons, right? That at some early point, it just thermalizes and we cannot extract any information anymore. But instead, we have the problem that it's much harder to detect. So yeah, so in principle, this is the picture. But then, as we already mentioned, right? There's some questions to be answered, right? To actually do this in a quantitative way. And these are the questions we will be discussing in a lecture. So you need to think about what actually are possible sources and how strong is the signal that they would give you. Then you need to think about propagation, right? So how do the gravitational waves propagate through this entire universe? How are they sensitive to the evolution of cosmology? And then detection. Right? How do you actually, at the end of this entire process, detect these gravitational waves? And if you've answered all of these three questions, right, then you can go back to this big picture and see, okay, can you actually learn about particle physics by looking for gravitational waves? Any more questions on that picture? Okay, so then let's get to some serious stuff. So now we really want to, for today's lecture, we're basically focusing on this propagation part, right? So we will assume there is a gravitational wave, right? And we'll talk about how that gravitational wave was sourced tomorrow and on Wednesday. So for today, we just assume we have a gravitational wave, and we're interested in understanding how it propagates through the universe and what it even really is, a gravitational wave, right? We always say it's a perturbation of the metric, but let's try and understand what that actually means. So we start with Einstein's equation. Because at the end, what we're doing is simply gravity. So I'm not going to derive it. I will explain it, but I will assume that you've seen this beforehand. So on the left-hand side, here we have the metric terms. And on the right-hand side, we have the energy momentum terms. Okay, g is Newton's constant. C is the speed of light. For the moment, I will keep it. At some point during the lectures, I will set it to 1. But I will try and keep it as long as possible. And all these terms on the left-hand side, right? So here we have the metric. We have the Ricci tensor, and we have the Ricci scalar, which in terms are both functions of the metric. So once you know the metric, you can compute the entire left-hand side, right? So this is describing the curved space-time. And the only input you need to compute this is the metric g mu nu. On the right-hand side, this thing is the energy momentum tensor. And it's describing the matter, the entire matter content, energy content of the universe, right? So what this equation is telling you is that the matter content curves space-time, and vice versa, it is telling you also kind of how the curved space-time impacts any matter particles, right? So how things propagate in curved space-time, right? So this, all what these equations are about is about telling you the interaction between some matter content of the universe and the space-time of the universe, that these are not two independent things, but they have to obey these equations. Okay, and of course, I mean, in general, yeah, these are Lorentz indices, right? So this is a set of equations, right? It can be arbitrarily complicated to solve in a general context. Now, luckily, we're interested in a much simpler situation here. We're specifically interested in a small perturbation from flat space-time. Okay, so we're going to consider this metric here, g mu nu, to be flat metric, and the sign convention I'll be using is the GR sign convention, so minus plus plus plus, because we'll see in a second it makes it much easier to do these computations, though I know in particle physics you want to do it the other way around. So half my papers are on this convention, the other half is in the other convention. It's a complete mess. Plus a small perturbation, which we call h mu nu, right? And small means that all entries in h mu nu should be much smaller than 1. So that's the situation that we're interested in. And for the moment, we will focus on the left-hand side here, right? Because that's all we need to compute the left-hand side. In particular, because for most of today, we'll be interested in propagation vacuum. And in vacuum, the right-hand side is simply 0. Okay. So. Okay, so let's compute the left-hand side in this perturbative expansion. So we start with, starting from the metric, we can first compute the Christoffel symbols. So that's, okay, they're just defined as derivatives of the metric, so have, this is still the completely general expansion, g mu sigma, del nu g beta sigma plus del beta g nu sigma minus del sigma g nu beta. Now we want to go to this limit here, okay, where I should also say, I mean, this is obviously constant, right? This can depend on the point in space-time. So clearly, all these derivative terms will only pick up the h part, not the g part. So if I want to expand in h and get something which is first order in h, the only terms I'll get is if I put the h here, sorry, put the eta here, put the flat space-time here, and put the h here, right? That's the only terms I can get that are first order in h. So we just do replace here eta, and replace here g goes to h. Everything else is the same. And then this is the result to leading order in H, so there will be corrections of order H squared, which we will drop. So for reference, for example, when the sensitivity of LIGO is the gravitational wave's amplitude of about 10 to minus 20, 10 to minus 24. Okay, so the correction factor that we're dropping here is really absolutely tiny, unless you're very close to the source, right? If you're very close to the emerging black holes, right, then it's a different story. But when we're talking about propagation and detection, this is absolutely and completely safe. Okay, once we have the Christoffel, we can compute the curvature tensor. So more indices. So this we get, again, definition, just by taking the derivatives now of the Christoffel symbol. So del alpha gamma mu nu beta minus del beta gamma nu alpha plus gamma mu alpha sigma, yes, gamma sigma nu beta minus gamma nu beta sigma gamma nu alpha. Okay, so the open indices should be these four, and the sigma should be contracted everywhere. Okay, now the first term to observe is that this term, right, the leading order term was order H, right, which means if we have gamma squared, this is already H squared, right, so we get rid of these terms because they're order H squared. So we're only left with these two terms. So let's take this one, right? So we take the derivative with respect to alpha of this line here. So again, the derivative acting on eta can give nothing, right? So we have to have the derivative acting on the second part. So we get 1/2 eta, this guy, mu sigma, and then del alpha acting on this, right? So del alpha del nu H beta sigma plus del alpha del beta H nu sigma minus del alpha del beta H nu beta. And then minus, now comes the second term, but the second term is exactly the same as the first, right? Just the only difference is that alpha and beta, right, have been interchanged, right? So it's the same term, but with alpha and beta interchanged. But now you see we have this term, right? So this term is symmetric in alpha and beta because I can just compute the derivatives. So if I have this term and I have minus with the same but alpha and beta interchanged, right? Exactly, this cancels. So we only have 4 terms left, right? 1, 2, and then again 2 here in the with alpha and beta interchanged. Okay, and now we're nearly there, right? Because from the Riemann tensor, we can now compute the Ricci tensor, right? Which is the one that we need here. So the R mu nu, by just contracting, right? R alpha mu alpha nu. Okay, so we just contract this index with this index. And then we contract again, right? So this to get the Ricci scalar, right? And we contract with a metric, so G mu nu R mu nu. Okay? I'm not going to go through this explicitly, right? I mean, I think you get the idea. And it's just a matter of shoveling around indices, right? And then throwing out the terms that are symmetric or anti-symmetric, depending on which contraction you're doing. Oops, no. Go here. Okay, but if you do that, right, so you take this result, you contract again. Here when you do this thing, right, you remember you only want to keep terms in leading order in H. And then what you finally get for the left-hand side of Einstein's equation, right, so if it is G mu nu, is minus 1/2 box. So box is just del alpha, h bar mu nu. So this h bar, this is just introduced for basically just for having the notation a bit shorter. So it's defined as h mu nu minus 1/2 eta mu nu h, right? Where this h is just h mu, right? So the trace of the h mu nu that we've been considering. So this is sometimes referred to as the trace reduced h mu nu tensor. If you write it in that way, the expression just becomes shorter, so it's convenient. And we'll see later that in certain conditions the trace vanishes, and then it's anyway just the original gravitational wave. Okay, so box plus eta mu nu del rho, del sigma, no, yeah, well, del sigma del rho, I need both of them, h bar rho sigma minus del rho del nu h bar mu rho minus del rho del mu h bar nu rho. Okay, so mu and nu should be the free indices, sigma and rho should be everywhere contracted. Yes. Okay, so this is the left-hand side, right, of our linearized Einstein equations. So let me give this a reference. So if we're just in vacuum, right, we would set T mu nu to 0, which means we just have that this expression equals 0. Now, it still looks a bit nasty, but I'm telling you this already looks much better, right, than kind of the full non-linearized Einstein's equation. It would look even more nicer, right, if we could get rid of these 3 terms here, right? Because this thing is just that would be just a free wave equation, right? That's kind of what you're expecting when you expect to describe a gravitational wave just by name. But there are still these other terms, right? So we do need to think about what they mean, and if we have a way to get rid of them. Okay, any questions to this point? Any indices that I got wrong? Yeah, yes. Okay, where? Up, down, left, right? Ah, right. I'm gonna check, right? That should be, yeah, right. Delta alpha, delta sigma, right? Yeah. Good. Anything else? Ah. Ah, right. And 2 mu's is not good, right? Which one is it? Yes, this is a sigma. Good. Thank you. Yeah, so luckily, once we get to the end of today, we'll have simplified the gravitational wave tensor to the point that we don't need Lorentz indices anymore. Okay, so to get any further than here, we need to talk about gauge invariance, right? And the reason we need to talk about gauge invariance, well, is because we cannot ignore it, right? It's unfortunately if you have a frame dependence, right? This is GR, right? GR kind of always depends on which observer, which frame, and so on. But also because you see that a lot of these terms, they have derivatives, like they have d rho h mu rho, right? So if we could do something similar as in electrodynamics, right? If we could kind of impose the thing to be transverse, if we could put something like Lorentz gauge, these terms would all disappear, right? So, but it's also, okay, so there will be, it will be first complicated, but then it will simplify things. But also it's simply that we have to be sure that the things that we compute are either gauge invariant, right? Or that we fixed the gauge consciously in a way that we know that we fixed it. So let's talk about gauge fixing and scalar vector tensor decomposition. Okay, scalar vector tensor. And so to do so, let's look at the symmetries of the problem. So we started with GR, right? And GR is of course invariant on the general coordinate transformations. Okay, this is nothing new. But now what did we do, right? We linearized our equation, right? I said well, don't worry about it, right? H is tiny, 10 to minus 20, right? We're not making an error here. However, what does it mean? What does it even mean when I said that H mu nu is smaller than 1, right? I mean, what that somehow means is that I need to introduce, in general, my initial matrix may not even be exactly flat, right? It may also have some planets, some solar system in it, right? So in order to even say my perturbation is small, I need to define some sort of time slicing. And on each time slice, I need to be able to do an average to determine my background metric, right? And then I can say my perturbation is small with respect to the background metric, right? If the background metric is completely flat, right, it is a bit trivial. Already, if you have an FRW universe, right, so universe is expanding, right, you've broken the symmetry a bit between time and space, right, because you've introduced a scale factor which depends on time. But even more so if you're in some general realistic curved background, you can only define the background metric as kind of the time independent or the spatially independent part by performing this time average, or it's performing the spatial average on a time slice. So we did a step here when we went to perturbation theory. So when we linearized, or when we said, okay, we're going to say that H is small, right? So in the moment where we said that G is eta plus H and H is small, we introduced this time slicing, right? And that means we broke the invariance and the general coordinate transformations, right? Because we've kind of sliced space and we did the average only in one direction. So that means that instead of the full general coordinate transformations, we only left with the invariance on the SO3 global spatial rotations. Oops. Okay, so yes, H is tiny, right? Yes, neglecting higher order corrections in H is fine. But simply the step of going to a perturbative expansion, of saying something is small, broke the underlying symmetries of the theory. And then we did another step, because not only did we say, okay, we're going to take H to be small, but then we say we're just going to forget really about everything which is higher order in H. So we're really just going to stay with a linearized theory. And if we go to in a linearized theory, then you can do, if you think about it, you can do a kind of a Fourier expansion, right? And in linearized theory, different types of Fourier modes don't mix. So that means that I can take properties under these global spatial rotations. In particular, I can identify things that rotate as scalars, vectors, or tensors, right? Meaning they have 0, 1, or 2 indices under these rotations. And these different sectors, the scalar, the vector, and the tensor sector, won't mix, right? And that is because we've linearized, right? That's only true because we're strictly considering things only to first order in H, right? So then we have SVT decouple. right? Where this was scalar vector tensor. So how does that work in practice? Right? So if you're a mathematician, right, you can take this more schematic way of thinking and turn it into some group theory discussion, right? If you're a physicist, right, your life is easier. So what this means in practice is, take, for example, G mu nu, right? And then the first step, right, the step of kind of saying, okay, I distinguish between time and space, is just that I write my general tensor, right, G00, G0I, Gi0, Gij, and I draw some lines, right? So it basically means I'm going to distinguish between the time component, the zero component, and the spatial component, right? They're no longer exactly on the same footing. And then when I do the second part, right, when I do the decomposition, I'm now just going to consider each one of these objects, right? And I'm going to see, is it a tensor? Is it a vector? And how can I perturb it by staying in that same class? Okay, so let's do an example. So the second step of that schema is, okay, I go, say, G00. Okay, G00 has no spatial index, right? So it's a scalar in our notation, right, on the SO3 rotations. So this means if I now want to ask, okay, what can this metric look like? There's going to be a background part, right, which is -1. And now I can perturb it only by a scalar, right? Because I cannot add something here that is indices, right? Because it would just not make sense, right? I cannot have something without indices here and something with indices here. I cannot have a scalar and perturb it by a vector, right? It just doesn't work. That's the second part, right, about the decoupling, at linear order, the decoupling of the different types of perturbations, right? So I'm just going to write this, can add one scalar perturbation, let's call it phi, and then for convention, people put a 2 here. Okay, and that's the only way, the only perturbation that I can add into this G00 component. Then I can go to Gi0, right? So this is this guy or this guy. And then I can perturb with the, so now at leading order this will be 0, right? In the flat metric this is 0. And now I can write this. Okay, I'm putting in, because later we will want to do this not only in flat metric, but also in FRW, right? So I'm putting in the scale factor now, but for the flat metric case, just put the scale factor to 1, right? So 2a, where, well, I mean, a is basically 1 for what we're doing now, because we're in flat space. And then we can add a vector, and how can we add vectors, right? We can either just add the vector itself, or we can add a derivative of a scalar, right? So I can add del I of some scalar, right? Let me call that scalar b. Or I can directly add a vector, which is itself an index. And really being a vector means that has no scalar component, right? So del I Si equals 0, right? Otherwise, it would have that Si would have a scalar component. Okay, so we can add, basically we're trying to, on the right-hand side, just construct things which have the same index structures on the left-hand side, right? And we can do that by either taking a scalar and taking a derivative, or we can do it by adding in just a vector. And these are going to be two new ways, independent ways that we can perturb the metric. Sorry, say again? Oh, yeah, yes, plus, sorry, yes, that made no sense at all. That was just the background part, right, and this is the perturbed part. Okay, and then we have the IJ part. So in flat space, right, this would just be a squared, the scale factor if we have so, or just 1, delta ij, right? That's the flat part. And now we can perturb, right? How can we perturb? So we can keep the delta ij, right? But add a scalar perturbation here, phi. Or we can take a scalar, but take 2 derivatives, right? So del I, del j of f. Or we can take a vector, right? Let me call it t, and take 1 derivative, del I tj, and then to make it symmetric, del j ti. Or we can add directly something with 2 indices, so a tensor perturbation. Okay? And again, we have to make sure that the vectors that we're adding are pure vectors, right? So they have this transverse condition, and the same for the tensor, right? So for this tensor object, we will impose that del I t I j is 0, and also that the trace ti is 0. Again, the reason is that otherwise you would have a component inside this tensor object which is secretly a scalar or a vector. Okay, so now let's do some counting, right? So here we started off with a symmetric 4x4 matrix, right? So how many degrees of freedom in a symmetric 4x4 matrix? 10. Okay, and now we count, right? So scalars that we added, right? So we added phi, we added b, we added f, and we added psi. Okay, so 4 scalars. Vectors, right? We added si and tj, so 2. And tensors, we added 2. Okay? So now we count 1, sorry. 1 tensor, right? The tij. So now we count degree of freedom, right? So we have 4 from the scalars. Now, a vector has 2 degrees of freedom, right? So plus 2 times 2. A tensor also has 2 degrees of freedom, right? So in total, 10. Okay, as it should. Okay, I mean, this is just a sanity cross-check that we haven't forgotten any terms. But really, this is just kind of a somewhat manual way of figuring out what sort of perturbations I can put in my metric and what sort of properties they have in terms of rotation properties or transformation properties under this symmetry. Okay, I think there should be questions. Right, in principle it can be non-perturbative, right? And if it is non-perturbative, that's also fine, right? And indeed, in some sense, so this is still general, right? So this you could even do if we did not linearize, right? Now, the advantage of the linearizing is that essentially you'll have, if you now look at how things evolve, right, you'll have a big block of evolution equations, right, for all your degrees of freedom. And now the scalars will kind of couple among themselves, right, and will evolve. The vectors will couple among themselves and evolve. And the tensor will be all by itself and evolve, right? So which exactly. So here we're not, well, okay, right. So maybe let me put, right? So we're not really using it, right? But we're kind of anticipating that we will be able to use it. And hence we're already decomposing into scalar, vector, and tensor, right? Because then that will be useful later, because in the linearized theory, we know that these sectors evolve independently. And hence it is a useful way of writing the perturbations. Yeah. Yeah. Exactly. Yeah, exactly, exactly, exactly. Because basically, like for example, the trace of a tensor, right, is secretly a scalar, basically just because it has no indices, right? So we just kind of want to subtract all the things out that don't actually have the transformation property that we're looking for.
About the global rotation. Why can't you use global Lorentz in space? I mean, this is
Okay, I think in flat, if you're strictly in flat space, right, then I think you probably could. But moving forward, we're not going to be strictly in flat space, right? We're going to have a background and a perturbation, right? And the background is not going to be perfectly flat, right? It's going to kind of have galaxies and that sort of stuff in it, right? So we really have to do this time averaging step. But in fact, I mean, you do still have Lorentz transformations, but they're they're only the small ones, right? You can kind of only have the infinitesimal Lorentz transformations in the linearized theory, right? Whereas initially you had all coordinate transformations. Any more questions? I promised you it would get complicated, then it would get simple. We're now in the step where it gets complicated, and you're asking, why the hell are we doing this? What do I not need anymore? Maybe that. Okay, so that was kind of identifying scalar vector and tensors, right? So far we haven't actually talked about any gauge fixing or using any gauge symmetry, right? We've just decomposed, right? We haven't gotten rid of anything yet. We've just made it look a lot more complicated and introduced a lot of new letters. Now let's talk about gauge invariance. Right, and here I mean gauge invariance in the GR sense, right, which meaning the invariance under these types of coordinate transformations. So take an infinitesimal coordinate transformation. Some x mu goes to x mu plus epsilon mu. So this is some small shift. And now we can do the exactly same thing that we did before for the g mu nu. We can also do it on the epsilon, right? So this epsilon will have a zero component, right? And it will have a spatial component. The zero component will just be a scalar. And the spatial component, we can either have a derivative of a scalar or we can have a vector, right? With the same properties as above, right? So this should be a true vector, right? So del I fi equals 0. This is a scalar. So what does that mean? That means that using infinitesimal coordinate transformations, I can shift things by 2 scalar and 1 vector degree of freedom, right? Which means I can also use these, if I want to fix a gauge, right? I can use these coordinate transformations to choose a specific gauge, which means that from this full set of perturbations degree of freedom we had here, I should be able to remove, by using the invariance on the infinitesimal coordinate transformations, I should be able to remove 2 scalars and 1 vector. So 2 scalars, 1 vector can be gauged away. And also, an interesting note here is that there's no tensors here, right? So one and only tensor that we had is gauge invariant. under these transformations. Okay, so now you can look for a gauge fixing condition which fixes these degrees of freedom and consequently removes the degrees of freedom from this full set of perturbations. Okay, and the gauge fixing condition that is used is the Lorentz condition. Right, so Lorentz gauge. So del nu h bar mu nu equals 0, right? And you can show that if you start with some general set of perturbations, that you can always use this transformation to fulfill this condition. Okay? So, and also, I mean, here, 2 scalars, 1 vector, right? That's 4 degrees of freedom. Here we have 4 equations. Well, I mean, these indices should, we put them up, right, so that you see what is contracted. 4 equations to remove 4 degrees of freedom. So we started off with 10, right? Minus 4, now we're only left with 6. At this point, we're left with 6 degrees of freedom. And in particular, if we now look up at the G mu nu up there, right? All the terms, everything but the first term vanishes, right? Because all the other terms disappear once we put this condition, right? And now, that means with this equation up there, just becomes box h bar mu nu. And then on the right-hand side, if we're in vacuum, it's 0, and otherwise we just have the energy momentum tensor. So this is what we call it a gravitational wave, right? Because this is a wave equation, right? So this is really the gravitational wave equation, right? And where did it come from? If you just recap, it came from taking Einstein equation and linearizing it, right? That's essentially all that we did, being a bit careful about gauges and symmetries. So linearized Einstein equation. And this describes, what does it do? It describes both. So if we set the right-hand side to 0, right, then that's just a free wave equation. So that's the propagation of gravitational wave. If we set the right-hand side to non-zero, right, we're including source terms. So that also describes the sourcing of gravitational waves, right? So this equation describes sourcing and propagation of gravitational waves. Okay, any questions? And so now you see kind of why it is important to keep track of, well, one of the reasons why it's important to keep track of the gauge invariance, right? Because instead of this complicated equation, we can now work with a much simpler equation. But we have to keep in mind, right, that we did some gauge fixing, right? Which means that our results now are no longer gauge invariant, right? They're only true in this gauge, which is fine, right? Because at the end of the day, whatever we want to compute is supposed to be a gauge invariant observable, right? So we can do the gauge fixing. We don't have to work with the full gauge invariant theory, but we just have to remember that we did some gauge fixing, right? Because we need to be aware that any intermediate step we look at, which is not strictly a gauge invariant observable, will now be gauge dependent. Yes, there is a residual gauge transformation here. Yes, that'll be the next step. Yes, 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 absolutely. Any other questions? Okay, then let me answer this one, right? Because that's an excellent question. Okay, we no longer need this. Yes, so indeed, right, exactly as in electromagnetism, right, Lorentz gauge leaves a residual symmetry, right, some residual gauge fixing to be done. So let's start for simplicity in vacuum, right, so T mu is 0. So now you can see that I could add another epsilon prime here, right, just shift by another epsilon, and if box of this epsilon prime, right, is 0, then that does not disturb this Lorentz condition, right, in vacuum. So that means I still have the residual freedom to do any further coordinate transformation with any epsilon prime that matches this condition, right? But this condition is again 4 equations, right? Which means I can do the kind of the same logic as above, right? I can also this epsilon prime, I can write as 2 scalars, 1 vector. So with this residual gauge freedom, I can always remove another 2 scalars and 1 vector. So I can remove another 4 degrees of freedom. Now in vacuum, that's particularly simple, right? I mean, I can always do this, right? I mean, the counting of degrees of freedom does not depend if I'm in vacuum or not. The explicit form of the gauge fixing condition does, right? So in vacuum, so I can always remove 4 degrees of freedom, and in vacuum, I can do it in a particularly convenient way, right? So again, minus 4 DOF, right? So now I'm at 2. 6 minus 4 is 2. And in vacuum, the way we do this is called transverse traceless gauge. And the conditions are that H bar, so the trace, right? The trace, let me put the indices, right? Mu is 0, so traceless. That's one condition. And H0ij, H0i is 0, right? So meaning everything that has a 0 component is 0, right? So 1 equation, 3 equations, right? So it's 4 equations, it removes 4 degrees of freedom. That's kind of a convenient way of doing it in vacuum. You can also do it if you're not in vacuum, right? Just then you cannot use this explicit form of gauge fixing, right? You have to do a different form of gauge fixing, right? But you can always remove the other 4 degrees of freedom using the residual gauge symmetry, and you're always left with 2 degrees of freedom. So in this transverse traceless, right, which is also called the TT gauge, right? What does that mean? So for starters, because the trace is 0, right? This means, probably erased it. Yes, no, it's there. So H bar and H are the same thing, right? Because now the trace is 0 in this gauge. So we forget about the bars, and now we see that everything containing a 0 is 0, right? The trace is 0, I is 0, and it's transverse, right? This is basically, oh, wait a minute, this, yes, it's transverse, yeah. That's just from the Lorentz gauge, yeah. Del J, Hij, right? This is what the Lorentz gauge becomes when I've additionally added in this gauge. Okay, and what this means at the long end of the day is that this object, this Hij, is exactly the Tij that we introduced above, right? So it's the pure tensor degree of freedom, which is transverse, which is traceless, and it has 2 degrees of freedom, right? So now we can really understand that the gravitational wave, so A, it's a wave, right, in the sense that its equation is simply a wave equation. It is 2 degrees of freedom, and it's transverse. But in order to get that result, we had to do some gauge fixing steps, right? And if I'm not in vacuum, right, the same logic applies, just the explicit form of the gauge fixing of the residual gauge is different, right? You can still do Lorentz gauge, even kind of if you're close to the source or in the source, you can still do Lorentz gauge, but you cannot do TT gauge if you're inside the source region of the gravitational wave. So maybe let me just take a note. So if this is not 0, right, then what you would do if this is not 0, right, you would say, okay, you do the STV decomposition not only on the left-hand side, but also on the right-hand side, right? And so things will decouple, right? So it means at the end of the day, you're only interested in a tensor object, right, on the left-hand side, and you're only interested in a tensor object on the right-hand side. And then any gauge fixing condition has to take into account the tensor part of T mu nu, right, which is essentially the anisotropic part of the energy momentum tensor of the matter, right? So in this case, how do I write it? Maybe, also, okay. Also 2 remaining degrees of freedom, but explicit gauge fixing is simply more complicated. But also, you don't have to fix the residual gauge, right? I mean, you can also happily have some gauge, you can still have some gauge freedom in there, right? It's completely fine, right? You just kind of need to keep track of what you're doing. You can even do, if you want to make your life hard, you can do the full thing, right, in a completely gauge invariant way, right? You don't have to gauge fix anything, right? You can keep all 16 degrees of freedom all the way to the end to your observable, right? You will get the same result. It's just a lot harder to do. The question? Yeah. Equal. So 6 minus 4 is 2. So the 6 is what we got here, right? So we did first 10, Lorentz gauge removed 4, and this residual gauge removed 4, so we're left with 2 degrees of freedom. Any more questions? Okay, so now maybe a question, so now we're 1 hour in, do you want a short break? Yes. Okay, so to just, recap what we did before the break and to add one last comment on gauge invariance and frames, right? Because, okay, so we started from Einstein's equation, we linearized it, we thought a bit about gauge fixing, and we arrived at that wave equation, right? And many times, if you hear a gravitational wave lecture, right, that will just be the starting point, right? And kind of, well, why do you need to know all the rest? But the reason I think you do need to know all the rest is that very often, kind of in the end, the discussion is just done in this TT frame, right? And kind of, okay, everything becomes simple, and we'll show in a second, I'll show you kind of explicitly what things look like in a TT frame, right? And largely, that's sufficient, right? But there are some cases really where it's not. And there are some cases when there's a lot of confusion because of kind of, well, we've done some gauge fixing, right? So kind of our results that we have, the expressions that we'll have for the gravitational wave are gauge dependent, right? And so we have to be a bit careful. So the 2 frames that people typically consider, right? So, I mean, I call them frames because other people call them frames, right? But really it's just a statement about the gauge dependence due to the gauge fixing that we've done, right? So the 2 frames that people usually consider are the TT frame. So the advantage of the TT frame, the physical meaning of the TT frame, okay, so now we just introduced it, right, by doing some gauge fixing, right? It actually also has a very nice physical interpretation, and the physical interpretation is that in the TT frame, the coordinates are defined by freely falling test masses, right? So that's not obvious, right? It's not obvious at the moment that that gauge fixing, right, corresponds to that physical interpretation. But you can show that's exactly what it means. So let me. Right, so recall that all the gauge fixing that we did, we're not actually ever gauge fixing the tens of degrees of freedom, right? There's no gauge invariance in the tens of degrees of freedom, but we're gauge fixing the scalars and the vectors, right, in the metric. And that corresponds to kind of fixing, corresponds to the way that we define the coordinates in a given frame, right? So in the TT frame, the statement is that the physical interpretation is that the coordinates are freely falling test masses. The gravitational waves takes a beautifully simple form, right? It's transverse, it's traceless. There's no other components in a metric apart from really this Tij component that we had initially. It also has the nice property. The GW is simple, right? It also has the property, and this we will actually derive tomorrow, I think. Is that if, but this it's related to the statement here, right? So okay, maybe this is the way we'll do it. So now I'm just telling you this, right? Just an information, right? Coming from nowhere. Tomorrow we'll show that in this TT frame, if you have particles initially at rest, then even with the passing gravitational wave, they will stay at rest, right? Which essentially translates to this statement, right? So we'll show tomorrow, at the moment it's just an information, but tomorrow we'll show that that's actually what this frame means, right? That if you define the gravitational wave in this way, if you do this gauge fixing, then you get this property for free-falling particles. But there's a problem, right? And the problem is that a rigid body appears to be oscillating in the presence of a gravitational wave, right? And the reason is that, okay, the physics is the coordinates of free-falling test masses, right? So if I want to describe this table in the presence of the gravitational wave, the table is completely rigid, right? It's not going to move at all with the gravitational wave. But my coordinate frame, right, as the gravitational wave comes, is going to be wobbling around. So if I now describe this table in this coordinate frame, it's going to appear that the table is wobbling. But the table is not wobbling, right? So there's kind of a fake, well, it's not fake, I mean, it's there, right? It's just, it's a frame-dependent statement, right? But kind of this TT frame has you have to be careful because it means that rigid bodies appear to be oscillating with the gravitational wave. Right, and I stress appear and rigid, right, because the statement is exactly something that is not supposed to be responding to the gravitational waves, appears to be moving because of the choice of frame. So that's a beautiful frame for theorists, right? Because everything is simple, your expressions are simple, your equations are simple. It's a frame an experimentalist would never choose, right? You'd never choose to describe the table in a coordinate frame, which is moving around, right? So the experimentalist will instead use what is called the proper detector frame. Or also Fermi normal coordinates, right? So you kind of, and that's really the frame in the lab, right? So the frame in the lab is really, I define myself a rigid ruler, even a hypothetical rigid ruler, and I just measure my distances with this rigid ruler. And then a rigid body just is a rigid body, and there's no confusion, right? So in this case, so coordinates defined by rigid ruler. And that means that if I have a freely falling test mass and the gravitational wave comes, right, that test mass is just going to move with the gravitational wave, right? So the gravitational wave will correspond to essentially a Newtonian force on the test mass, and we can see that, right? Whereas here, since the coordinates are freely falling test masses, right, kind of the gravitational wave will apparently have no effect because it's kind of the effect is already in the coordinates, right? So here, GeV acts as a Newtonian force and again, tomorrow we'll look at kind of geodesic equations and we'll explicitly see this behavior, right? But I just wanted to tie it now into this discussion of gauge invariance, right? Because this is fundamentally where these differences come from. But the issue is now that we can not, I mean, it's a different choice of gauge fixing, right? So in particular, this last step, the way we dealt with the residual freedom, right? I mean, that just led to this choice, right? And here it's just a different choice, right? You do for Fermi normal coordinates, say the metric is flat at one particular point in space, and you expand around that point in space, right? And the result of this is that the gravitational wave simply looks more complicated. There's nothing wrong with it, right? You can write it down. It just doesn't take this very simple form, and in particular, you still have entries in all the zero components, right? The whole tensor, it's still only 2 degrees of freedom, but those 2 degrees of freedom are no longer kind of nicely in your two transverse modes, but they're all over the place, right? Your entire tensor is populated with entries, which of course all depend on each other. So it's just not so nice to do a computation, but it describes the physics that, it directly describes the physics that the experimentalist would measure in the lab, right? And there's nothing right or wrong about either of the frames, right? I mean, both frames are completely correct. The computation is completely correct, right? The prediction is completely correct. You just have to then at the very end, when you decide what are you actually measuring, what is your, I mean, if you at the very end, you compute a gauge invariant observable, it will be the same, right? But if you have something which is maybe not a gauge invariant observable, you need to just be careful that that you realize whatever you're computing, how that is connected to the thing you actually want to measure in the lab, right? And maybe it's not exactly what you thought it was. Okay, so that's just a word of caution, right? Because this is the source of confusion, or has been a source of confusion. But this is where it comes from, right? It comes from this entire story about that, well, GR has coordinate invariance, right? And we did some gauge fixing, and we just have to be aware that we did that gauge fixing. Okay, so then, I don't know what number I'm on, maybe 4, I don't know. Let's now, from all this kind of abstract gauge fixing and symmetry and frame story, let's actually get back and actually look very concretely of how this gravitational wave, that with these constraints, right, what it actually looks like. This is not here. So, plane wave solutions. So now what we're actually going to do now is we're going to go to vacuum, right, T mu nu 0, and we're just going to solve the wave equation in the TT frame. Okay, so we know how to solve a wave equation, right? So that's the wave equation. So we can just solve it with an ansatz. H mu nu of x is A mu nu of k sine k alpha x alpha. I've dropped the, of course, there's also so that's just the amplitude of a Fourier mode, right? I've dropped the phase because not relevant at the end. And then, of course, we can just plug it in. Derivative acts in here, right? So we get k alpha, the amplitude, and the sign. Now in vacuum, this should be 0. And so the condition is that this, right, which is just e squared minus p squared, has to be 0. So this tells us, not surprisingly, right, that the object we're describing is, well, it's a wave, right? Here's the oscillating function, and it propagates with the speed of light. Okay, now we can explicitly do TT gauge, right? So the TT gauge will impose conditions on this guy, right, on the amplitude. So let's consider, for example, some wave vector here going in the z direction. So what does it look like, right? So we have some 4x4 matrix. We know from the TT gauge fixing that everything with a 0 component has to be 0. Then we know it has to be transverse, right? So meaning also, oops, in the z direction, we're going to get only zeros. Now we're going to use that it's traceless, right? So AXX has to be minus AYY, and we're going to call this H plus, right? So we have H plus minus H plus. And then we're going to use that it's symmetric, right? So AXY is AYX, and we're going to call this H cross. So we have H cross, H cross. Okay, and this is I mean, for a given Fourier mode, right, this is just a constant. Okay, so we see that there's just two polarizations, right? I mean, as of course we already knew, right, because there was only 2 degrees of freedom up there, and these 2 degrees of freedom appear in this very explicit way in this matrix for a wave vector which is simple, right? Otherwise, of course, you need to rotate if you have some general wave vector, right? And so we see explicitly that it's transverse, and we see explicitly that we have 2 degrees of freedom and how they appear. And these 2 degrees of freedom we will now always refer to as H plus and H cross. And this is what I meant, that at the end of the day, we don't need to deal with Lorentz indices anymore, right? Because we only have the plus and the cross polarization, and all other Lorentz Lorentz indices have been absorbed. Actually, we're doing it today. Okay, did this thing, excellent. Yeah. Okay. So now we know explicitly what the gravitational wave looks like, right? Now, and this actually brings me back to this frame discussion, right? I thought I was doing it tomorrow, but apparently I'm doing it today, Monday morning. And so the question is, how do test masses react to this gravitational wave? Okay, so let me maybe remove this here. So this was still general, right? Particularly if I put a bar here, right? And this thing here, right? This was the TT gauge assumption, just to see what it explicitly looks like. Okay. So now let's look at the effect of the gravitational wave on test masses. And we'll have 2 test masses, right? One at x and one at x plus psi. So to understand how the gravitational wave acts on the test masses, we need to look at the geodesic equation. Which tells you precisely how do freely falling test masses respond in a curved background. And a gravitational wave is formally nothing else than a curved background. So the geodesic equation tells you that dx squared d tau, right, where tau is the proper time along the geodesic, is the Christoffel symbol dx nu d tau d d sigma d tau equals 0. And now let's do a quick detour to what I was trying to get at up there. Consider test masses. So this is a slight detour, but we'll get back to this equation in a second. So consider the fact that test masses initially are at rest, right? So let's consider some initial dxi d tau is 0, right? So test mass at rest. And then this equation here just becomes d squared xi d tau squared minus gamma I 0, 0 del x 0 del tau squared. Okay, just because I basically removed all of these derivatives, right? So I'm only left with those equal 0. And now the statement is that you can now evaluate this guy, right? The way we did it, well, now it's gone, right? But beforehand. So this will depend on the gravitational wave. And the expression, if you plug everything in that we had before on the board, is just 2 del 0h 0I minus del 0h 0, 0, which in the TT frame is 0, right? So TT, 0. Okay, so this tells you that in the TT frame, a test mass initially at rest stays at rest, right? And that is kind of why these test masses are a good way to, I mean, this is why the test masses are basically the coordinates of the TT frame. Okay, that was just an aside, because above I just gave you that as a statement, right? But this is how you actually compute it. Oh, I didn't want to do that. So this was kind of a TT frame insertion, right? But now forget about it again, and we go back to this equation. Because what we actually wanted to understand is the general response of test masses to the gravitational wave. So this describes how one particle evolves on the geodesic, right? But one particle is not enough, right? I need the two particles because I want to be able to describe kind of how the two particles move relative to each other once the gravitational wave passes, right? Because one particle, I mean, I can always kind of change coordinate system, right? And gauge the effect away. So we need to go from the geodesic equation to the geodesic deviation equation, right? Which means we write this equation for xi, for x, we write this equation for x plus xi, and then we say xi is small, and we expand to first order xi, and that gives us kind of for two nearby geodesics, how kind of the test particles moving along these geodesics respond to the gravitational wave. So geodesic deviation equation to first order in xi, right? So you just do this equation again with the shifted x, and subtract one from the other. So what you get is d xi d tau squared plus 2 gamma mu nu rho evaluated at x dx nu d tau dx rho d tau plus xi del sigma rho mu nu sigma of x del x nu del tau dx rho d tau is 0. And now, okay, just to confuse you, right? I mean, here I did this little inlet about the GT gauge, right? But I am actually, I mean, I want to describe kind of, you know, the gravitational wave is passing, and I want to describe how the particles move, right? So I really don't want to do that in the TT frame, right? Because in the TT frame, the particles are just not going to move, right? So I can still get all the physics of observables in the TT frame, right? And if we have time, we can talk about how to do it, right? But if I really want to visualize how the particles are moving, I better choose the proper detector frame, right? Because in a proper detector frame, I really get the motion of the particles. So in the proper detector frame, right, we're expanding, I mean, we're doing these Fermi normal coordinates, we're expanding around a given point in space-time, and at a given point in space-time, one point only, I can always set the Christoffel symbol to 0. Okay, so what we're going to do is we're going to say that this guy, right, is 0. So the Christoffel symbol at point x is 0. That's always something I can do. And that is, in fact, proper detector frame. This I cannot set to 0, okay? Because I can only set it to 0 at one point, which means in particular I cannot set the derivative to 0. So I have to keep this one. And we're also going to assume a non-relativistic detector, or non-relativistic motion of the particles. So our test masses are going to move non-relativistically. So that means that dxi over d tau should be much smaller than dx0 over d tau. Okay, and then this equation simplifies a lot, right? Because here, okay, this entire term is gone. And here, I only need to keep the 0 components. And so then I just get that psi second derivative is Riemann tensor, and we just have the I0J0 component. J, okay? So this guy is basically, like, you put this a simplification in here, and then you see that the combination that you've left is this component of the Riemann tensor. So now you see that you have really the time. So here you really see kind of, here you have the motion of the particle, right? The second derivative, so the acceleration, depending on something on the right-hand side, which depends on your gravitational wave to the Riemann tensor, and depends on the position or the separation of your particles to this guy. So this is now really a Newtonian force, okay? Because this is the acceleration, right? So this tells you how the gravitational wave acts as a Newtonian force on your particles. And so the only thing we're now left to do with, right, is to evaluate this guy. And now, here, in principle, we know how to evaluate this, right? I mean, I gave you the expression for the Riemann tensor in terms of the gravitational wave. However, in principle, you know, here we're working in a proper detector frame, so I should evaluate this guy also in the proper detector frame. However, luckily, the Riemann tensor is gauge invariant to first order in H. Now, that's a fun exercise to do at home. I wanted to give it as an exercise, and I started doing it, and it's absolutely horrible, right? But this guy, so I'm just going to give you his information, right? So this guy is gauge invariant to first order in H, which means we are allowed to evaluate it in whatever frame we want. And in particular, we can evaluate it in the TT frame, where our life is much easier. Okay, so this thing is gauge invariant. And so we can evaluate it in the TT frame. And we get that Ri0ji is just minus 1 over 2 c squared hij second derivative tt. Okay? So if you work in a proper detector frame, you should at the end get the same result, right? So you should get some expression which you identify as the tt expression, but the statement is general, right? So despite that now we're working in a proper detector frame, we have an expression which actually depends on the HIJTT, right? But that simply happened because this thing is gauge invariant, right? And we chose to evaluate it in a frame that is easier. So if you understand what you're doing, jumping between the frames can actually simplify your life, but you have to be careful to not make a mess. So then the final expression here is, that this is 1/2 h double dot tt psi j. Okay, so this tells you how the gravitational wave impacts the test particles in the proper detector frame. And it really kind of shows you that the gravitational wave is acting as a Newtonian force. Right, which is basically how, in words, what I had announced beforehand for the proper detector frame. And this is an important equation, so it gets 2 stars. Okay, questions on this? Yeah. No, that's actually the... No, I think this is the normal time derivative, right? Read dt, not d tau. Now I need to think why. Let me think why until next time. Okay, so then the very last thing for today, let's see what that equation actually means concretely. So now we can take the gravitational wave from up there, right? So just a plain gravitational wave in the TT frame, right? Incoming in the Z direction. And now we want to see what is this response, right? And because here's the HIJTT, right? So that was okay, right? So I can just get the response by plugging that solution in here. And then we can just solve the equation. Yes, am I maybe missing a... Okay, what happened? So I should be getting that by shifting the Christoffel symbol by zeta, right? And then subtracting off the one where it's not shifted by zeta. Right. Right. So I expanded the Christoffel in zeta, right? And then I acted with the derivative on that. Does that make sense? That's the... But in the Christoffel or in the X? Just in the second term. Yeah. Well, but the question is, why is there no zeta here, right? Shouldn't there be a zeta somewhere? You think, is it just a... Do you think one of these should be zeta, right? Yes. Yes. Yes, okay, right. Here, okay, yeah. So here, thanks. So here, right, so here I've just expanded the zeta in the second term, right, in the derivative, right? And here I've expanded the zeta in the Christoffel. Yes, thanks. Yeah, sometimes when you're in front of the board, you don't see these things anymore. Okay. So let's solve this equation for plugging in this gravitational wave, right? And so now let's forget about, the 0 and the z direction, right? Because nothing is happening, right? Everything is 0. So let's take the plus polarization as an example, right? So HTT AB, right? Where AB now is just x and y. Okay, so that's just from above h plus sine omega t h0, 0, minus 1. The zeta, right? We're just going to expand. We're going to consider some particle x0 plus delta x of t, y0 plus delta y of t, right? Where x0 and y0 is just the position of the particle without the gravitational wave. And now we have the incoming gravitational wave. We want to know how does it shift, right? So meaning we want to solve this equation to understand what we get for delta x and delta y. So we do that, right? We take the equation and look at the first component, right? So x double dot, right? So of course this is 0. So we just get delta x double dot. And then we get minus h plus over 2. Okay, the 2 time derivatives give me the omega squared. The sign, of course, stays. And then I get the x plus delta x, right? So now I need to take, right, I take this matrix, contract it with this, right? So I just get the first component back in the x direction, right? And now I'm just going to drop the delta x. Delta x is small. Okay, and this is then my solution for delta x. Well, this is the equation for delta x, double dot, right? And then I can solve this, of course. And we know how to solve an equation like that, right? With delta x over here, and here we just have the sign. So we simply get, we simply cancel the omega squared, right? Or the minus omega squared. So h plus over 2, x 0, and the sign function, right? If I take 2 derivatives of that, get 2 powers of omega down, and a minus sign, clearly get this. Okay, and then we can do the same for delta y, right? The only thing that changes if I do delta y is that I get this minus sign. So the solution will be the same, just that I get a minus sign, and of course here I get y0 instead of x0. Okay, so what does that mean? This means, imagine I have a bunch of particles in the xy plane, right, sitting on some circle. So this particle here, right, for example, has only x0, no y0, right? So if we consider the part of the phase where the sign is positive, then this will just shift outwards to here, and this on the left will shift to the left, right? Because it's just shifting proportional to y0. In the y direction, the same, just with the minus sign, right? Which means that this particle will shift down, and this particle will shift up. So if we're in the part of the sign where the sign is positive, we're going to deform the circle into an ellipse, which looks like this. And if we then continue the gravitational wave evolves, we go to the phase where the sign flips sign, we get the opposite, right? So we get an ellipse, which is deformed in this direction. Okay, and now you can see that this shape, right, so kind of the circle squishes to the kind of this type of motion. This is essentially a cross, right? So this is why we call this is why the name plus polarization, right? That we just called it like that without motivation earlier. And you can do the exact same story, of course, for the cross, right? You go through the exact same exercise. Now, instead of the diagonal matrix, you have the off-diagonal matrix, right, with 1 and 1. So that means the motion in x will depend on the y position, the motion in y will depend on the x position. And what you will get is that your circle kind of gets deformed, but in the other way, in the literally the cross way, right? So the circle kind of squishes. In the plus mode, the kind of circle squishes like this, and in the cross mode, the circle kind of is rotated by 45 degrees, and then squishes in the other way. And these are the two polarizations of the gravitational wave, right? So this is kind of equivalent to the electromagnetic wave when you say you have a plane wave and it's polarized, I don't know, in x and y, right? These are kind of the two orthogonal polarizations of the gravitational wave, and that's what they kind of literally look like. And that's really the physical effect you would have if you just imagine a bunch of freely falling test masses and you have the incoming gravitational waves. That's how the test masses will react to the gravitational wave. And that's, for example, how the mirrors in LIGO react to the gravitational wave. Okay? And that's then how you get the observable effects due to gravitational waves. Okay, I think I'll stop here, but happy to take any more questions. Right, so it's coming in this direction. Yeah, yeah, yeah. Yeah, so here we also see it's transverse, right? Because the motion is purely transverse to the incoming gravitational wave. Yeah. They're independent. They're independent. It's really like what you can have. I mean, a priori, right? It's like for the photon, right? You have the two linear polarizations and they're a priori independent. That's the 2 degrees of freedom that we have. And it's the same here. You have this, and they are independent. Now, you can have, of course, a particular source. I don't know, an in-spiral of a black hole, right? And then, of course, the source will be such, right, that the two signals will be correlated. But a priori, if I don't know anything about how the gravitational wave was sourced, they're independent. Any more questions? Maybe just to mention, so people often work in what they call the chiral basis. So that instead of the plus and cross, they use left and right. So if you want to do that, you get them as some normalization h plus minus a h cross, right? That gives you the, say very similar as for electromagnetism, right? Where you can also work in the linear or in the polarization basis. You can do the same here. And then you get the complex coefficients. This is a little bit more physical, because here, in some sense, you know, if you take your coordinate system and you rotate it by 45 degrees, this turns into this. Okay, so there's kind of nothing inherent about a source that only has plus polarization, right, versus a source that only has cross polarization, right? It's just a way of parameterizing the two independent degree of freedoms. But again, it's exact same thing for electromagnetism, right, where you have a linear polarized wave, linearly polarized in two directions, right? Of course, you can rotate your coordinate system and then one becomes the other, right? There's no physical meaning really in one over the other, but the physical meaning is that you have two independent polarizations.